Hello to all, welcome to the channel Money's Gate Tech Vision. In this video, I am going to solve gate problems from the subject Signals and Systems for the discipline of Electronics and Communication. I have taken the GATE 2024 question paper and I have taken the topics which is common for electrical, electronics and instrumentation engineering. So all those branch candidates can watch this video. So let me start solving the problem. So first I will read out the problem. First problem, a causal and stable LTI system, linear time invariant system with impulse response h of t produces an output y of t for an input signal x of t. This is for one LTI system. They have given the input and impulse response. A signal x of 0.5t is applied to another causal and stable LTI system with impulse response h of 0.5t. Then the resulting output is. Okay, so they have given the conditions for two LTI systems. They have given the conditions for two LTI systems. So we need to solve for the resulting output. Okay, so let me write the system output first. See here, this is for first LTI system. They have given the input as LTI system. They have given the input as x of t and h of t is the impulse response. Then output will be y of t. We know y of t is nothing but the convolution of x of t and h of t. X of t is input, h of t is the impulse response of the LTI system. And for another LTI system, they have given the input as x of 0.5t and impulse response is h of 0.5t. We need to find the resulting output. So we know output should be the convolution of the input and impulse response. So it should be the convolution of x of 0.5t and h of 0.5t. So we need to find this convolution. So here I am going to use the convolution property. I am going to use the time scaling property of convolution. So by using the time scaling property of convolution, x of at, convolution of x of at and h of at, if a is the scaling factor, then output will become 1 by modulus of a y of at. So I am going to apply this formulation to solve for resulting output. Okay. So here, therefore, we can find the convolution of x of 0.5t and h of 0.5t. So here the scaling factor a equal to 0.5. So we can substitute that 1 by 0.5 into y of 0.5t. So which is equal to 1 by 0.5 is 2y of 0.5t. This is the answer. This is the resulting output for the another LTI system. So answer is 2y of 0.5t. So option A is the correct one for this problem. Okay. So let me move to the next problem. So what is the next problem? It is taken from the Z transform. For a causal and discrete time LTI systems with transfer function, one transfer function h of z is given. Which of the following statements is or true? Okay, so this is the keyword is or true means multiple, there may be multiple correct answers. Okay, multiple correct options. So it is a MSQ type of question. This is a MSQ type of question, that is multiple select question. More options will be correct. So we need to check with the options. So what are the given options? The system is stable, the system is stable, and then second option is system is a minimum phase system. Third option is initial value of the impulse response is given as 2. The fourth option is final value of the impulse response is 0. So we need to check with each options. So we will check with the each option. First, let me write the h of z, and let me find out the poles first. Poles and zeros. So given h of z equal to 2z square plus 3 by z plus 1 by 3 into z minus 1 by 3. So let me find the poles and zeros. With that poles and zeros, we can check for stability and minimum phase system first. Okay. So to find out the zeros, the numerator factors. Numerator should be equated to 0. Let me find the factors for numerator. 2z square equal to minus 3. Z square equal to minus 3 by 2. Therefore, z equal to plus or minus j root 3 by 2. So these are zeros. And then for poles, we can write directly. See the numerator factors z plus 1 by 3 and z minus 1 by 3. So poles are z equal to plus or minus 1 by 3. Or the poles. Okay, so let me check with each options. Option A is the stability condition. We will check with the, we'll go with the first option. Stability. So what is the condition for stability if h of z is given? All poles, all the poles should lie inside the unit circle. Okay, let me check that. Should lie inside the unit circle for the z plane. See here, this is the z plane, real part of z, and then imaginary part of z. So let me draw the unit circle first. So here 1, this is minus 1, this is the unit circle representation. Let me check with the poles. What are the poles? Z equal to plus or minus 1 by 3. So 1 by 3, we can mark here. This is minus 1 by 3 and this is plus 1 by 3. So all the poles are lying inside the unit circle only. So the system is, we can say this system is stable. This system is stable only. Okay, so option A is the correct one. So let me pick out the first option. And let me check for the second option. Okay, let me check for the second option. What is the second option? The system is a minimum phase system. Minimum phase system. Minimum phase system. So for the condition for minimum phase system is all the zeros should lie inside the unit circle. Should lie inside the unit circle. Okay. So let me check out that. So let me draw the unit circle. This is real part of z, imaginary part of z. So let me draw the unit circle first. So this is 1, minus 1. So let me mark the zeros. So what are the zeros? Z equal to plus or minus j root 3 by 2. So 3 by 2 is 1.5. Root of 1.5 is approximately equal to 1.2 only. So 1.2 means we can mark here and here. This is minus j root 3 by 2 and this is plus j root 3 by 2. So here all the zeros are lying outside the unit circle. Okay. It is not lying inside. It is lying outside. They are lying outside the unit circle. So this is not a minimum phase system. Option B is incorrect. It is wrong. Okay. We can mark it as incorrect. And then let me check for the C option. So what is the option C? Initial value of the impulse response is 2. So let me use initial value theorem for h of z. Initial value theorem. Okay, initial value of impulse response means h of 0. we need to find h of 0. So by using initial value theorem, limit z tends to infinity of h of z. So let me apply the h of z here. Then limit z tends to infinity 2z square plus 3 z plus 1 by 3 into z minus 1 by 3. So when we apply the infinity, it will become 2z square by z into z. Okay, constant values can be discarded. So z square and denominator z get cancelled. It will be equal to 2. The value is equal to 2. So we got the initial value h of 0 equal to 2. So option C is also correct one. Option C is also the correct one. So let me check with the last option, final value. What is the last option? Final value of the impulse response is 0. So we can use final value theorem to find out the final value of the impulse response. Final value of the impulse response means we need to find h of infinity. So formulation is limit z tends to 1, z minus 1 into h of z. So let me apply h of z here. So limit z tends to 1, z minus 1 into h of z is 2z square plus 3 by z plus 1 by 3 z minus 1 by 3. So when we apply the limit z tends to 1, this factor, it becomes 0. 1 minus 1, it becomes 0. 0 into anything is 0 into anything is 0 only. So we got the final value h of infinity as 0. So last option is also the correct one. Last option D is also the correct one. The final value of the impulse response is 0. So here in this multiple select question, A, C and D are the correct options. Totally 3 answers for this problem, A, C and D. Okay. Let me move to the next problem. This problem is taken from the Fourier Transform. Consider two continuous signals x of t and y of t as shown below. So here one x of t waveform is given and y of t waveform is given. If x of f denotes the Fourier transform of x of t, then the Fourier transform of y of t is. So we need to find the Fourier transform of y of t. So here x of f denotes the Fourier transform of x of t means Fourier transform of y of t can be represented as y of f. So we need to find y of f from the signal y of t. First, we need to find y of t in terms of x of t. How this input x of t is changed to y of t. That we have to check with the basic operations on signals. That is folding, is it folding or shifting or scaling? That we have to check it. Okay. So let me draw this and we will find out the y of t signal in terms of x of t. So first I will draw the waveform. So this is the input waveform, -1, -0.5, 0, x of t. So let me reverse the amplitude. We are having 1 for the output signal. So amplitude reversal. First amplitude reversal operation. Then the waveform will become like this. -1, in the middle -0.5, 0. So amplitude got reversed. We can represent this signal as minus x of t. And then shifting or delaying by 0.5 seconds. Let me delay by 0.5. Then the waveform will become like this from -0.5 to 0.5, in the middle 0. Amplitude is 1. So we can represent this as minus x of t minus 0.5 or t minus, I am taking that as fraction. Okay. t minus 1 by 2. Minus x of t minus 1 by 2. Now check with the output what we are having. What time we are having? See here. Minus 2 to 2. So here we are having minus 0.5 to plus 0.5. Okay, the signal should be expanded. Signal should be expanded. So here 0.5 into 4 equal to 2. We will get 2. Minus 2 to 2 into 4. So into 4 means we have to give that as fraction. Okay, so the output waveform, we can scale it by 1 by 4. We can scale it by 1 by 4. Then the signal will be expanded from the time minus 2 to 2. Okay, this is minus 2, 0, 2. When it is scaled by 1 by 4. When time is scaled by 1 by 4. So, x of t by 4 minus 1 by 2. The signal will be represented like this. Okay. Now, we can represent y of t. We got the same y of t. Minus 2 to 2. So, here also, in the question also, we are having the y of t like this only. So, we can represent y of t in terms of x of t as minus x of t by 4 minus 1 by 2. So, let me simplify this. When we simplify this, it will become t minus 2 by 4. Okay. So, let me take this to find out y of f, which is Fourier transform of y of t. We need to find y of f. Okay. Y of f. So, what is y of f? Integration of minus infinity to infinity y of t e power minus j 2 pi f t into dt. Okay. So, here I am going to use this y of t in terms of x of t. So, for simplification purpose, let me take this t minus 2 by 4 as u. Okay. Let me take t minus 2 by 4 equal to u. Therefore, t minus 2 equal to 4u. Therefore, t equal to 4u plus 2. I am going to change the t variable to u variable. Change that. So, I am going to change t variable as u variable. So, for that, I am simplifying like this. T minus 2 by 4 equal to u. And then, therefore, t minus 2 equal to 4u. So, therefore, t equal to 4u plus 2. So, if I am going to change the limits means, if t equal to infinity, if variable is changed, limits also has to be changed. U is also infinity. If t equal to minus infinity, u is also equal to minus infinity. When we differentiate on both sides, it will become dt equal to 4 into du. Okay, so let me write the equation for y of f. Y of f equal to, in terms of x of t, minus infinity to infinity, x of only shifting operation, x of t minus 2. Okay, I am taking this only. I am going to use this and this to solve the problem. X of t minus 2 into e power minus j 2 pi f t dt. Now I am going to change the t variable to u variable. So, it will become integration of minus infinity to infinity. What is t minus 2? It is equal to 4u. So, I have changed the limits also. Limit is same limit only. When t equal to infinity, u is also infinity. If t equal to minus infinity, u is also minus infinity. So, limit, there is no limit change. So, t minus 2, we will equate to 4u. And then e power minus j 2 pi f, in the place of t, we can substitute this one. In the place of t, we can substitute this one. Okay, 4u plus 2 into, in the place of dt, we can substitute 4 into d. Now, y of f equal to integration of minus infinity to infinity, x of 4u e power minus j 2 pi f 4u plus 2 into 4 into du. Okay. This is minus x. Folded signal now. This is minus x. So I am taking minus 4 outside. I am taking minus 4 outside. So minus infinity to infinity. X of 4u e power. Now I am expanding this exponential signal. E power minus j 2 pi f into 4u into e power minus j 2 pi f into 2. Okay, into du. Now, minus 4, I am taking this outside, e power minus j. E power minus j, 2 into 2 equal to 4. So, 4 pi f. The integration of minus infinity to infinity, x of 4u, e power minus j 2 pi f into 4u du. Okay. Now, observe clearly. So what is this equation? This formulation is nothing but the Fourier transform. If the signal is x of t means Fourier transform is x of f. The now signal input signal is x of 4u. So we can represent that Fourier transform as x of 4f. We can represent like that because we are having 4u here and here also 4u. So here also du. So we can represent this as minus 4 e power minus j 4 pi f into this is nothing but x of 4f. X of 4f. Okay. X of 4f. Now, let me check with the options. Minus 4 is here. E power minus j pi f. So, it is not the option. Option A is incorrect. Let me check with the B option. Minus 4 e power minus j 4 pi f x of 4f. So, option B is the correct one for this problem. So let me move to the next problem. This is the easiest problem. The radiant frequency values for which the discrete time sinusoidal signal x of n is given a cos ohmian plus pi by 3 has a period of 40 is or dash. This is also MSQ type of questions. This is also MSQ type of question, multiple select question type. So we need to check with the options. So first let me find the radiant frequency and then we will check with the options. Okay. So let me check with the, first let me find the frequency. So here x of n equal to a cos ohmian plus pi by 3, where ohm is a fundamental frequency. So here ohm is a frequency. Here T naught is given as 40. So we need to find the frequency which is represented as omega naught or ohm naught, which is equal to 2 pi by T naught. So this that is equal to 2 pi by 40. This will get cancelled 1 by 20, which is 0.05 pi radians. 0.05 pi radians. So this is the fundamental frequency. Okay. So maybe this is the fundamental frequency or multiples of 0.05 pi are also the frequencies. Okay. The radiant frequency values are. So we need to find the multiples of 0.05 pi. So let me check with the options. Let me check with the options. There is no 0.05 pi. So we need to check whether the given options are multiples of 0.05 pi. Let me check one by one option. So here, let me check with the first option, A, that is given as 0.15 pi. So 0.05 pi is the fundamental frequency into 3. 5 into 3 is 15.15 pi radians. So option A is correct one. This is a multiple only. And then let me check with the B option. 0.05 pi into 45, I think. 45. Maybe 25 2. Okay. Into 45 equal to 225. But it will become 2.25 pi. So he given is 0.225. It is not a multiple of 0.05 pi. So option B is wrong. So this option B is wrong. Let me check with the C option, 0.3 pi. 0.05 pi, 5 into 6 is 30. So into 6 equal to 0.30 pi. So we got the answer. So C is also correct. And then let me check with the D option. 0.05 pi. 5 into 9 is 45. So 5 into 9, 45. 2 decimal places, 0.45 pi. So we got the answer. Option D is also correct. So for this problem also, A, C and D are the correct options. Multiple select question type. Okay. So we solved 4 problems from GATE easy paper. This is Mani's GATE Tech Vision. This is Mani's GATE Tech Vision. This is the channel for engineering lectures, and you can subscribe to my channel. You can view the lecture series freely, and thank you very much. If you have any queries, you can mail to me dmoneylecture@gmail.com. This is my mail ID.